Hello everyone, this is Mr. Kaviani, and by the end of this video you should be able to describe the effects of gravity on objects in motion, describe the motion of objects that are in freefall, and calculate the position and velocity of objects in freefall. In a moment, we're going to watch a video clip of a bowling ball and a bunch of feathers being released from rest at the same time. I'd like you to make a prediction about which one you think will hit the ground first, and why. It's important to note that this will be under normal conditions. Pause the video and take a moment to jot down your thoughts before moving on. We're going to watch another video clip, but this time the bowling ball and feathers will be released inside of a vacuum, meaning all of the air in that chamber will be removed before they're let go. How might this change your prediction for which object, if any, will hit the ground first? Take a moment, pause the video, and jot down your thoughts here before proceeding. Please note, the video you're about to watch is in slow motion. Objects do not really fall this slowly. Alright, so hopefully what you've just witnessed in these two video clips has given you an idea of how objects behave when acted on solely by gravity. Meaning, if we can ignore air resistance and friction, then all objects fall towards the center of the Earth with the same constant acceleration, regardless of their mass. The bowling ball and feathers obviously have very different masses, but when we removed the air, and gravity was the only force acting on those objects, they accelerated or fell at the same rate and sped up at the same rate as well. We call this falling without air resistance or friction free fall, and we'll use this term frequently throughout the course. Now, because objects that fall freely through space do accelerate as they fall, right? They don't travel at a constant speed. They actually do speed up as they fall. We proved that in our lab. We call this the acceleration due to gravity, right? Because gravity is the force causing this acceleration. We'll talk more about gravity as a force in our next unit, but for now, just know that we call this value lowercase g or little g. And we've measured little g to be a value of 9.80 meters per second squared. This is a constant that you'll be given always. It does depend slightly on latitude and altitude, so the further you are away from the Earth's surface, the less strong this force is. But we'll use this value for all of our calculations in this course. And so on the right, I have an image too of a hammer and a feather being dropped. This is another famous experiment actually done on the moon. Hammer and feather being dropped in the vacuum of space, and they both fell at the same time as well. So this is not just an Earth thing. This happens anywhere there is a gravitational field. All right, now when it comes time to solving problems using gravity, it's important to keep mind of a few things. The first is when you define your coordinate directions, we're going to call up positive most of the time, and then down negative, again, most of the time. So I would show that on my coordinate axis here with a positive up and a positive right, just in case that's relevant as well. So what this means is that for our acceleration value, right, in our kinematic equations, instead of a, we can actually use little g, which is equal to 9.80 meters per second squared. And it's important to make sure, because I'm calling down negative, and since the force of gravity pulls things right down towards the center of the Earth from our perspective, this acceleration is also in the negative direction. And so if I'm calling down negative, I'll need to indicate that with a negative sign here. So this will be negative 9.80 meters per squared. This is a value we will use frequently in our problem solving. It's also important to keep track of our displacement. Our displacement will be negative then for an object that falls, essentially. So if I were to look at this image here on the right, I have a ball. This ball is falling towards the earth, and so it's falling down. I would maybe indicate this as perhaps 100 centimeters, and then maybe the ground would be 0 centimeters. And so for this object, it's delta y in this case, and I'm going to use delta y instead of delta x because we're dealing with vertical displacement, would be negative 100 centimeters. Essentially, my y final minus y initial would be 0 minus 100 centimeters. So just keep track of your position. Your position should be decreasing or becoming more negative as well. All right, the last important tip when solving problems with free fall is that the velocity of an object thrown upwards at its maximum height is going to be equal to 0 meters per second. And this is an important assumption that isn't necessarily intuitive. Whenever we throw an object up into the air, we notice it slow down before eventually it comes to a stop for the briefest of moments. You can't notice it with your the naked eye, but as that object rises, it slows down, stops, and reaches some zero velocity, and then eventually changes directions and speeds back up on its way down. However, it's important to note that at the maximum height, its velocity is 0. This is an important piece of solving problems whenever you're asked to solve for example, the maximum height an object will reach or the time it takes to reach its maximum height. So please feel comfortable with this assumption. All right, please take a look at the next video for an example of solving a problem with free fall.